Okay, welcome everybody. Hope everybody had a good day today. Today we're going to be nearing the end of our study of DC circuits. We're going to be concentrating on combination DC circuits. We've already had some exposure and the sound. We've had combination. We had experience with sound. What we're going to do that's going to be a little bit different tonight with combination circuits is that we're going to apply a procedural approach to solving combination circuits rather than an intuitive approach. Okay? And so what I want to do is first draw the simplest form of a combination circuit. And the simplest form of a combination circuit would be some kind of a electromotive source connected to a resistor, which is then connected to two resistors that are in parallel with each other. So that would be the first of the parallel resistors. This would be the second of the parallel resistors. So if this was the source voltage, and let's just give it a value of 12 volts, and this were resistor 1, this were resistor 2, and this were, fix that, and this were resistor number 3, then that would constitute a combination circuit. Now the reason that it's a combination circuit can be described in a number of different ways, but I think the easiest way to describe it is to take a look at resistor number 1 and ask ourselves the question, is resistor number 1 in series or in parallel with resistor number 2, or is it something else? And the answer to that question is, if we look at the series consideration, clearly resistor 1 cannot be in series with resistor 2, because if there's a current flowing through resistor 1, the current flowing through resistor 2 couldn't possibly be the same, because by Kirchhoff's current law at this node, the two currents coming together have to equal the current coming out through resistor 1. And the definition of a series circuit, as we know, is that the current is the same through all components. So they can't be in series. Nor can they be in parallel. The reason they can't be in parallel is because, as we've learned in the past, when we have two components that are in parallel, their voltages end up being the same. Okay? When we go around a closed loop. Like, for instance, if we go around this closed loop, this resistor and this resistor are in parallel because they're the only two components in the closed loop. However, if we go around this closed loop right here, what we find is that we have three components. We have an active component being the battery, and we have two resistors. And so Kirchhoff's voltage law would tell us that the voltage here must be equal to this voltage plus this voltage. Or stated in a more abstract way, the sum of the voltage drops around the closed loop must equal 0. The bottom line here is that resistor 1 is not in series or in parallel with resistor 2. So the question becomes, what is it? Okay? And one of the more useful techniques that I've found to describe what it is to just draw an imaginary dotted box around resistor 2 and resistor 3. And then taking a look at that imaginary box, we can say, well, if we consider the imaginary box as one lumped load, in other words, like if it were covered up and we didn't know what was in there, and we imagined for a moment that there was only one resistor in there, then clearly resistor 1 is in series with the imaginary box. Because whatever goes into the imaginary box has to come out of the imaginary box. And that's by Kirchhoff's current law. Okay? So it turns out that resistor 1 is in series with the parallel combination of resistor 2 and resistor 3. That's the way that you answer that question. If somebody asks you, how is resistor 1 related to resistor 2 in that circuit? Resistor 1 is in series with the parallel combination of resistor 2 and resistor 3. Now, for the purpose of analyzing combination circuits, what we're going to do is we're going to make a circuit that's a little bit more complex, and then we're going to come up with a logical sequential approach to solving the circuit. Okay, so this is going to be our example circuit. Let's say that we're given this following circuit. We have a DC source, and let's say that the source has 120 volts. And this DC source is hooked up to one resistor, another resistor, another resistor here, another resistor here, looping back to the source on the bottom, and then another branch over here, which happens to have 3 resistors in it. So we're going to call this resistor 1, resistor 2, resistor 3, resistor 4, resistor 5, resistor 6, and resistor 7. Now, when we're analyzing a circuit like this, let's say that we were being asked to find the current that was flowing from the source to the rest of the circuit, which would be the total current. Now this approach would also be applicable to anything that we would be asked to solve for this circuit. It could be voltage values, it could be resistance values, it could be voltage drops on the resistors, it could be power dissipations, it could be current flows through the branches. The set of procedures that I'm going to give you will apply to basically anything that you want to solve. But what we'll do for sake of simplicity is we'll just worry about solving for the current that's leaving the battery, okay, when we set up these procedures. First thing that we have to do is we have to give the resistors some ohmic values. So we'll say resistor 1 is 100 ohms, resistor 2 is 50 ohms, resistor 3 is 30 ohms, resistor 4 is 80 ohms, resistor 5 is 20 ohms, resistor 6 is 27 ohms, and resistor 7 is 42 ohms. Okay? Now, what we're going to do is we're going to look at this from the standpoint of what do we address first, what do we address second, what do we address third, and so on, in reducing the circuit so that we can solve it for anything that we might be asked. And it could be in this class, or it could be on an aptitude exam. It doesn't really matter. You still do it the same way. Okay, so what we're going to write here are the steps to solving a combination circuit. These are the steps. Okay? Step number 1. Step number 1 in solving a combination circuit involves reducing the circuit into its equivalent form. Okay? And so the first step that we're going to do is we are going to identify all of the resistors that are connected in series in branches of the circuit. So if we move back over to the circuit, where are the branches in the circuits? Or in the circuit, rather. This is one branch at the far right. This is another branch in the center. And those are the only 2 branches. So the branches are here and here. Those are the branches in the 2 circuits. So the first step that we have is we are going to combine series connected resistors in all branches. Okay? That's our first step. So, we're not actually going to do that yet, but we're going to look at it in terms of what we will be doing. And when we do that, if we come to the furthest branch to the right in this circuit, what do we find? We find three resistors, R7, R6, and R5. We can see that those resistors have a value of 42, 27, and 20 ohms, and they're clearly all in series. Okay? So would it be fair to say that we could substitute those three resistors with one single resistor and wouldn't affect the electrical characteristics of the circuit at all? Right. It would affect the topology of the circuit. It would look different, but it would not react any differently electrically. Okay? So that's our first step. Our first step is to do that. Then we look for another branch. And as we move from right to left, we find the second branch. In the second branch, we find two resistors, R3 and R4, and clearly those two resistors are also in series. Okay? And so a 30 ohm and an 80 ohm resistor are in series and could be combined by adding them algebraically and ending up with one resistor, and that would represent the same electrical effect as having the two individual resistors. So basically we've taken these three resistors over here and turned them into one. We've taken these two resistors over here and turned them into one. And so now we just have two resistors in parallel with each other. Okay? If we've done the first step, that's what we've accomplished so far. In the second step of our procedure, we combine parallel connected resistors. So going back to our circuit over here, clearly we had three resistors in series which could be combined into one. We had two resistors here which could be combined into one. That would leave us with two parallel resistors in these two branches. Those two parallel resistors could be combined into one resistor by using either the product over sum formula or the formula that says resistance total is the inverse of the sum of the inverses, right? And then that would give us one resistor. So in other words, if we went through the two steps that I'd indicated over here, combining the series connected resistors in all branches, and secondarily combining the parallel connected resistors, okay, then we would ultimately end up with one resistor over here. And that one resistor would represent the effect of R3, R4, R5, R6, and R7. Can everybody see that? Okay? And then finally, the third step would be to combine remaining series resistors. Combine remaining series resistors. Okay? So let's go back through it again real quick. Step number one, we take these three resistors and we collapse them into one. We take these two resistors, we collapse them into one. Now we have two resistors in parallel. We take those two resistors, we collapse them into one. Okay, using the appropriate formula. Okay? Now we have one resistor that's representing R3 through R7, and that one resistor is in series with R2 and R1. Can you see that? And so that's why our third step in the procedure is to combine remaining resistors. So ultimately what we're going to end up with is going to be a circuit that has a battery and one resistor. Okay? So let's go ahead and do that for this particular circuit. If we were to find the series total of R5 through R7, we could designate that as R5, 6, 7, and that would be equal to the algebraic sum of the resistors. So that'd be 20 ohms plus 27 ohms plus 42 ohms, and that would be equal to how many ohms? That would be equal to 89 ohms. We could then come to our second branch and combine resistors 3 and resistor 4. So resistor 3, 4 would be equal to the algebraic sum of those two resistors. So that would be 30 ohms plus 80 ohms, which would be equal to how many ohms? 110 ohms. Okay? So what we're going to do at this point is we're going to go ahead and erase these resistors, and we're going to substitute them with their equivalent resistance values. So resistor 5, 6, and 7, which were the furthest out, combined into one resistor. Call this R5, 6, 7, and that had a value of 89 ohms. And then in this branch right here, we had combined two series resistors which were labeled 3 and 4, so we'll call this R3, 4, and that had a total value of 110 ohms. Okay? Then, in the second step, we combine the parallel connected resistors. Okay? And so the parallel connected resistors would actually be labeled as R3, 4, 5, 6, 7, because effectively we're finding the electrical effect of all of those resistors connected simultaneously, right? And because there's only two resistors, we'll use the product over some formula, okay? So the product of the two resistors would be 110 ohms multiplied by 89 ohms divided by their sum, which is 110 plus 89. So what do you get when you do that calculation? 33 ohms?
Let's see. Oh, I probably added it up wrong.
49.2. 49.6?
49.19.
Okay, 49.2 is good enough for us. So we'll say 49.2. So if we were to take these two resistors and combine them into one resistor, that one resistor would have a value of 49.2 ohms. So this would be R3, 4, 5, 6, 7. 3, 4, 5, 6, 7. And again, the reason that we use this labeling technique is so that we make sure that we don't leave any resistors out. Okay? And that value was 49.2. Now, the problem is much simpler when we go back to step 3. Step 3 says combine remaining series resistors. Okay? So as we move back to the circuit, we see now that all we have are series connected resistors. And it's always going to work out that way. If you follow these steps and you do it in that order, it's always going to work out that way. Okay? And so if we combine those resistors, then we're going to have R1, 2, 3, 4, 5, 6, 7, and that's going to be equal to 150 plus 49.2. What's that? 100 plus 50 plus 49.2 ohms. And what is that? 199.2. So that's the total opposition to current flow for the circuit. So we can then erase all the resistors, or we could draw successively reduced circuits each time. Okay, it's just that we don't have enough board space to do that. And so we show then that as one total resistance, and we're just going to call this R total, which we know is the same as R1, 2, 3, 4, 5, 6, 7. And that has 199.2 ohms. Okay? And so going back to the original question, which was what is the current that's being drawn from the source, then we're simply going to use Ohm's law, right? Because we know that by Ohm's law, current is equal to what? Voltage divided by resistance, or the ratio of voltage to resistance. In our case, it's going to be the source voltage divided by the total resistance. So that's going to be equal to 120 volts divided by 199.2 ohms. And what's that going to be equal to? 0.6 amps. Or we could say that is 600 milliamps. Either way. Okay? So you can see that we started out with a circuit that looked a lot more complex than what we ended up with. We ended up with a circuit that looked fairly simple because there was only one resistor, one load. Okay? We started out with a circuit that had 7 resistors in it. And they were in a combination of series and parallel and combination configurations. Okay? Now, obviously, if the question was calculate the power that's absorbed by resistor number 7, then it wouldn't have been in our best interest to erase the circuit every time we simplified it. We'd want to redraw the circuit each time that we made another calculation. Okay? Because it's a lot more difficult to go back and redraw the circuit if you've already drawn it once and then you draw it in a simplified form, because you can come back to your original circuit and you can draw in, or you can write in whatever quantity you're looking for, whether it's current, voltage, resistance, or wattage. Okay, in terms of analyzing combination circuits, it really doesn't get any more difficult than that. And I highly recommend that you have these steps written down on your crib sheet. Because if you do them in any different order than this, you're going to run into problems. Right? I mean, if you tried to combine, let's say that you started at step number 2, and you tried to combine the parallel connected resistors first, before you had simplified the branches, you'd have a difficult time, right? Unless you were doing it in your head, which some people do. But if you want to show and be certain that your answer's correct, or let's say you're writing a computer program to analyze the circuit, then you would want to write it, according to this algorithm. Now, another thing, too, that I want to point out is the topology, or the way that circuits can be drawn, which sometimes can be very confusing, okay? But really can be simplified by just looking at them and asking yourself how Kirchhoff's current laws apply. Let's say that you were given a circuit that looked like this. You had a voltage source and a resistor, so this is resistor 1, it's 100 ohms, Okay? And then this came into a node, or a point. And then this point right here went this way, went straight down, went over this way, and went over this way. Okay? And on each one of these paths, there was a resistor. Resistor here, resistor here, resistor here, resistor here. Okay? And let's just say that each one of these were 1 ohm, 1 ohm, 1 ohm, 1 ohm. Okay? So this is resistor 2, this is resistor 3, this is resistor 4, and this is resistor 5. Okay? And then all of these resistors came back into a common node down here at the bottom. And then that returned back to the source. Now, we haven't looked at circuits that are drawn like that because it's not very symmetric. It's kind of curved and it's a little bit sloppy. Okay? But when we look at that circuit, what can we say about the relationship between resistors 2, 3, 4, and 5? They're all in parallel. Right. It makes no difference whether or not you draw it in an arc or you draw them in straight lines, like this. They're still in parallel. Okay? And so what I suggest is that if you're ever given a problem like this on an industry aptitude test or an exam in here, you won't be given a problem like that. Your book and the lecture notes give some problems like that just to make sure that you're straight on it. But whenever you're given a circuit like this, my suggestion is that the very first thing that you do is clean it up. So you take the circuit and you draw all of the resistors so that, you know, they're in a more conventional topographical form. Okay? So that they're drawn more like the circuit that we started with when we were talking about combination circuits. Now, there's one other topic that we need to talk about before we move on into some later sections, and that is this theorem of superposition. The theorem of superposition. The theorem of superposition says, the way it was explained to me the very first time it was explained to me in college, was that if I have a piece of paper, and I'm holding this piece of paper right here, and all the lights are turned off in the room. Now the room's pitch dark. There's no light getting through any cracks. Okay? Then the number of foot candles that are bouncing off of the surface of this scantron form, okay, are going to be 0 because there's no light. There's no foot candles. There's no photons being emitted. Okay? If, on the other hand, I come into the room and I have one light overhead and I turn it on, then it's going to illuminate my scantron, and my scantron is going to reflect a certain number of foot candles. In other words, the brightness of the scantron is going to be probably pretty dull because I'm in a big room and I've only got one light, but I'm going to be able to see it. Okay? If I turn on a second light, the number of foot candles that are contributed to the brightness of the reflection of the light bouncing off of this scantron is going to be the algebraic sum of the two foot candles that are contributed by each light independently. So in other words, they don't combine in some kind of a vector geometric way. They simply combine algebraically. Okay? So if I had 5 foot candles from the first light and 7 candles from the second light, then if I turned off the first light, I would expect to see 7 foot candles. If I turned off the first light, then I'd expect to see only the number of foot candles from the light that was shining. In other words, there is no constructive and destructive interference when it comes to measuring the brightness of the piece of paper or the Scantron or the tabletop or whatever it is that we're dealing with. The same thing applies to the concept of power distribution in an electrical circuit. So if I'm given a circuit like this, let's say that I have 2 batteries, and both of the batteries are 12 volts DC. And those batteries are connected to three resistors. And each of those resistors are in series. So this is resistor 1, this is resistor 2, this is resistor 3. And just to make the numbers easy, or easier, let's say that this is 12 ohms, this is 12 ohms, and this is 12 ohms. Well, actually, to show superposition, I should probably make them different. Let's say that this is 7 ohms, this is 9 ohms, and this is 41 ohms. So they're just arbitrary numbers of resistance or opposition to current flow. Okay. Now, clearly we talked yesterday about the effect of having 2 batteries that are connected in parallel. Okay, when we have 2 batteries that are connected in parallel and they're both rated at the same voltage, what voltage do we get out of that parallel connection?
Same voltage.
Do we get 12 volts or 24? 12, right. Because Kirchhoff's voltage law says that the sum of the voltage drops around the closed loop has to be 0, which means that because of the way these polarities are situated, the voltages are not additive or subtractive. Okay? The only thing that is additive is what? The current sourcing capability of the batteries. In other words, if there's a load that requires a lot of current, like for instance, you got a car in very cold weather and your starter motor, needs an extra boost of current to crank over and start your engine, then instead of having 800 cold cranking amps, by having 2 batteries hooked up in parallel, maybe you'll have 1,500 cold cranking amps for, 3 or 4 seconds. Okay, so these 2 batteries right here have the effect of being able to supply more current, but they have no effect on the voltage that appears downstream. The voltage that appears downstream is unaffected. Okay, so if we were to simplify this circuit, we could simplify this circuit by drawing our 2 batteries, and drawing one resistor. And that resistor would be the algebraic sum of these 3. So our total would be equal to 41 plus 9 plus 7. What's that equal to? 57. So that's 57 ohms. Okay? Now, if I wanted to calculate, given that these are still both 12 volts, if I wanted to calculate what the power dissipation was across resistor 1, 2, 3, which is the total resistance, what formula would be the easiest and most convenient formula to use? Looking at the Ohm's law wheel. Well, we haven't calculated the current yet. So is there a formula that doesn't, E squared R would be easier probably, yeah, because then we wouldn't have to calculate the current. So if we calculated E squared divided by R total, then that would be equal to 12 volts quantity squared divided by 57 ohms. And what would we come out with? So the total power would be equal to 2.52 watts. Okay? Now, if we did calculate the current so that we could come back and calculate the the power distribution in each one of these resistors, what would the current be flowing in that loop right there? We know that these two are in parallel, right? Because it'd be fair to say that this forms a closed loop. So if this is 12 volts, this has to be 12 volts, right? So what would be the current flowing through our total resistance? Would the current be equal to the voltage divided by the resistance?
0.21 amps.
Right, so that would be 12 volts divided by 57 ohms, which is equal to 0.2? 0.21 amps. Okay. Now, since these are equivalent circuits, would it be fair to say that the current here would be 0.21 amps? Okay. So if the current here is 0.21 amps, do I have enough information to calculate the power distribution here, here, and here?
Yes.
Okay. So let's first do this one. What would the power be absorbed by resistor 3? Let's just do it off to the side. The power on resistor 3 would be equal to 0.21 squared, I squared times R, times 41. What's that equal to? 0.21 squared times 41. 0.8? 1.8 watts. Anybody else get that? 0.21 squared times 41. 1.8. Okay. And then let's take a look at these two guys. How about the power that's absorbed in resistor 2? That would also be equal to I squared times R, which would be equal to 0.21 quantity squared times the resistance, which is 9 in this case. So what's that equal to? That's 0.4 watts. And then finally the power in resistor 1, that would also be equal to I squared R. So that's going to be 0.21 quantity squared times 7. And what do we get for that? 0.3. Okay? Now, let's take a look at this. Is it true that the total power is equal to the sum of the individual powers absorbed in the resistors? In other words, is the total power that's absorbed by these resistors right here equal to the power in resistor 1 plus the power in resistor 2 plus the power absorbed in resistor 3?
Yes.
And the answer is yes. I'm getting a little crowded for space there. But if we plug in 0.4, 0.3, and 1.8, what do we get? 2.52. Okay? That is the superposition principle applied to DC circuit analysis. Now, there are some questions where you can't solve the problem without knowing that. Okay? There are some things that don't combine algebraically in the study of electrical engineering. They combine in a linear fashion, or a nonlinear fashion. This is linear. Okay? The addition of power, or the distribution of power, in an electrical circuit is an algebraic phenomenon or a linear phenomenon. Okay? All right, so we've talked about combination circuits and the three basic steps to use to simplify any combination circuit, no matter how complex. Any questions on that? And then we've talked about the concept of the superposition principle. Superposition principle just says that the total power that's absorbed by a circuit is equal to the algebraic sum of the individual power distributions throughout the circuit. It's kind of a mouthful, but it's a good word bite for an interview. Excuse me, Mr. Jones, can you describe how the superposition principle applies to DC circuit analysis? Not an uncommon interview question. Okay. All right. So if there aren't any other questions, oh, okay, sure.
I recall in my circuit analysis, the topic of superposition had us deactivating sources. I mean, keeping sources active one at a time and then adding up the results together.
Yes. There are definitely times where that's the only way you can solve a circuit. And we don't have enough time for me to solve it, but I will show you a circuit where the only way you can solve it is to do exactly what you said. And what he said, for those that didn't hear, was I always thought that the superposition principle involved deactivating sources and then combining the result of the individual sources acting independently to get the total power. Absolutely true. Let's say that you were given a circuit that looked like this. Let's say that this is 12 volts, this is 7 volts, this is 100 ohms, this is 7 ohms, and this is 12 ohms. We'll call this guy R1, we'll call this guy R2, we'll call this guy R3, and what we want to know is the current flowing through resistor number 2. The only way you can solve that problem is to do exactly what you said. You have to deactivate one of the sources, considered a short because it's a voltage source, and then solve for the current flowing through that resistor. Store that number, write it down, okay? Redraw the circuit so that this 12-volt source is back in place, and then deactivate this source and replace it with a short because it's a voltage source. And then once you've done that, recalculate the current that's flowing through this resistor as a result of this source acting all by itself. Then you take those two currents and add them together, and that's the current that would be flowing if you built this circuit in the lab. So what you said is absolutely true. But it just depends on the circuit. It depends on the circuit and the complexity of the circuit. Any other questions? Okay? All right. Everybody drive safely and have a good night. If you have anything